All right, class. So we've been talking about covalent bond and Lewis structure and polarity. Now we're going to talk about the last part, which is hybridization. Now before we talked about that, let's kind of summarize what we talked about. We've talked about Lewis dot structure. And what was Lewis dot structure? Lewis structure, basically what they do is shows bonding, right? It will show you the bonding, what's bonded to what, how electrons are shared in covalent compound. Whisper theory showed you the geometry, if you remember that. So you would do Lewis dot structure to show the bonding, and then you would look at the whisper theory to figure out the geometry, the shape. Now the last thing we're going to talk about is valence bond model. Now what valence bond model does, it explains the interactions of orbitals in bonding. It explains the interaction of orbitals in bonding. Now, what does that mean? So, you know how like we said covalent bond is when you share electron, right? But can any two atoms share electron? So my friends make fun of me. This is how I usually try to set people up. My matchmaking skills is, oh, you're single, you should be together. But it never works, right? Just because two people are single doesn't mean they're gonna make it work. That's exactly the same thing. Not any two atoms can just share electron. We said covalent bond is sharing electron. You can't just take two atoms and say, yo, you two are going to share electron. They can only share electron if their orbitals overlap. So not any two non-metal can just share electron and form a covalent bond. Can only share electron if their orbitals overlap. So the orbitals have to overlap. So because of that, not every covalent molecule exists. Because not any two atoms can just share. You can share electron only if your orbitals overlap. You can't just be best friends with anyone, right? You have to have something in common. This is exactly the same thing. You can only share if they overlap. Now, let's keep going with this concept. Let's say, for example, I have H2. H2 exists, right? Now, why does H2 exist? Here's why. So H2, you have one hydrogen atom and you have one hydrogen atom. 1s and 1s orbital. Now, s orbital is spherical. S orbital is spherical. Okay? And then each one has one electron in a 1s orbital. When these two atoms come together, again, this is 1s orbital, right? 1s orbital. When these two atoms come together, their orbitals can overlap. So if their orbitals overlap, then what's going to happen? So they're going to overlap. And because the orbitals overlap, that means they can share electron. They can share electron because their orbitals overlap. Now, and the geometry that you get here, you get a linear geometry. So H2 exists because the two orbitals can overlap, and because the two orbitals can overlap, they can share electron. Let's talk about HF. Does HF exist? Yeah. Let's go over why HF exists. I have a hydrogen and I have a fluorine. Now, hydrogen is 1s orbital. Fluorine is going to be in a 2p orbital. Okay? Now, 1s orbital again. This is what 1s orbital looks like, spherical. Now, if you remember, 2p is going to look like a dumbbell, right? It's going to look like a dumbbell. Now, can these two overlap? Yeah, you can kind of see that it's easy for these two to overlap. So their orbitals is going to overlap. And if the orbitals overlap, you can share electron. So here again is going to overlap, and because it's overlapping, you can share electron. You can share electron. As you can see right here, the geometry would also be linear. Now here is a problem. So this is a great model. This is a great model. This model was valence bond model. The valence bond model says again, not every covalent compound can exist. It can only exist if they can share. If they can overlap, their orbitals can overlap so they can share electron. Now here's the problem. This is too simple. This is too simple, and this idea that the orbitals have to overlap, otherwise they can't share electron, it doesn't explain every covalent compound. So this is a nice model. Yes, the orbitals have to overlap in order to share, but it's too simple and it can't explain every single covalent compound that exists. For example, let's go over the CH4. It has carbon and it has hydrogen. Electron configuration for carbon is helium, 2s2, 2p6. Hydrogen is 1s1. Do you guys agree? Okay. So I have what I have here. I have 2p orbitals, and then I have 1s orbital. 2p. Oh, I did not just do that. Give me 1 second. It's 2p2. I got a little too excited. Okay. Now, carbon has 2p orbitals because you have 2 electrons in a p orbital. And 1 s orbital is for hydrogen, right? Again, 2p orbitals because you have 2 electrons, so you end up having, you have to use 2 of the p orbitals, and then hydrogen has 1 s orbital. Okay, so carbon has 2p orbital, hydrogen has 1 s orbital. Now, I have 2p orbitals, so I can, again, the p orbitals, they look like dumbbell, right? So 1p and then another p orbital. And then we said that hydrogen has s orbital. S orbital is spherical, like this. Okay? Now, this is great. The s orbital and the 2p orbitals are going to overlap. If you overlap, you can share electron. Here's a problem. Based on this, the predicted geometry looks like this, right? This would be the predicted geometry. If this theory, if this model was right, that you could only make covalent compound if the orbitals overlap. Here is orbitals overlapping. Carbon has 2p orbitals because it has 2 electrons in 2p orbitals, and hydrogen has the s orbitals, and they are overlapping really nicely. But if that was the case, this is a geometry we would get. It would look like a plus sign. But that's not the geometry of CH4. Geometry of CH4 is tetrahedral, right? This is the observed geometry. We know the geometry of CH4 is tetrahedral, is not just a plus. Now, what does that tell us? That tells us that this model is too simple. Model is too simple. That tells us that a model is too simple. Okay. Now, let's double check that you understand what we're talking about. So this model that we said, that the orbitals have to overlap. If the orbitals can overlap, they can share electron and they can form covalent bond, and you can have a covalent compound. That's a great model, but it's too simple. And the reason it's too simple, it doesn't work for every single covalent compound. It worked for H2, it worked for HF, but for example, if we have CH4, if we have CH4, so CH4, carbon has 2 carbon has 2 p orbitals because it's 2p2, so 2 of the p orbitals are occupied. And then we said hydrogen has s orbital. So if they overlap, what the geometry should be, it should like be a plus sign with a 90 degrees. But in reality, we know that the geometry we observe is tetrahedral. So the model was too simple. The model was too simple. We need a new model. So it's more than just overlapping orbitals. The new model is called hybrid orbitals. So it's a little bit more than just the orbitals have to overlap. Hybrid orbitals. What does hybrid mean? Every time I ask this, someone in class says, oh, I have a hybrid Toyota. Does not mean Toyota or Honda. Hybrid means mixing. Hybrid means mixing. So it's not just overlapping orbitals. We have to be mixing some orbitals. Okay? Now, let's go over what this means. We're going to go back to the CH4 example. CH4 example, carbon is in a center atom. Do you guys agree? Carbon in a center atom, 2s2, 2p2. Okay? Now, I'm actually going to write it out over here. So here I have a 2s orbital, and then here I have a 2p orbital. So this is 1, 2, 1, 2. This is for carbon atom. Okay. Now we said hybrid means mixing, right? Hybrid means mixing. Now I have a good example to make you understand it. Parents. If your parents want to come and talk to you, before parents go and talk to their kids, they have to be on the same page. If my mom and dad want to come and talk to me, if they're not on the same page and they're going to come and talk to me and tell me what to do with my life, that conversation is not going to go well because they have to be on the same page with each other before they come to me and they try to talk to me about my future. Right? So, again, this is like a non-chemistry example that helps. So if my parents want to come and talk to me, they have to be on the same page before they come and to talk to their kids. Otherwise, that conversation is not going to go well. This is exactly the same thing. If carbon atoms want to go and bond with hydrogen, if the carbon electrons want to go and bond with hydrogen, they have to be on the same page. If they're not on the same page, it's not going to go well. So they are going to mix. To be on the same page. So now each one is going to compromise. Each one is going to compromise and meet in the middle. And we end up having 1, 2, 3, 4 hybridized orbital. Again, if you're confused, that's okay. I want to explain this again. Hybridized orbitals. The hybridized orbitals, or the hybridized orbitals are on the same energy level. So this one had to compromise a little bit. This one had to compromise in a little bit. And then they end up making hybridized. They mix the orbitals together and make orbitals that are on the same energy level. Okay? Now that they're on the same energy level, they can go and bond with hydrogen. And 1, 2, 3, 4. So I needed 4 hybridized orbitals because I had 4 electrons. Okay, I'm going to explain this one more time. So before the carbon electrons can go and bond with hydrogen, they have to be on the same page, right? Your parents have to be on the same page before they go and talk to you. Otherwise, that conversation is not going to go well. So they're going to mix. They're going to compromise. And they're going to make energy levels that are on the same energy level. They're going to make orbitals that are exactly on the same energy levels. We call this hybridized orbitals because this one mixed with this one to form this hybridized orbital. Now I had 1, 2, 3, 4 electrons. So 1, 2, 3, 4 of these orbitals had to mix. Now when they mix, 1s orbital and 1, 2, and 3 of the p orbitals mix together. These and these, they all mix together. So what I call this sp3 because 3 of these and 1 of these mixed together because I needed 4. I needed 4 of these. These are hybridized orbital. Okay. So that these sp3 are gonna go now and bond with hydrogen. Now these new orbitals are gonna go and bond with hydrogen, and that shows the geometry that we actually get. Now I'm going to show you based on a picture. So here's what happened. I had an s orbital and I had 3 p orbitals. I had an s orbital. I had 3 p orbitals. They had to mix together. They have to combine together. They combined together and they generated hybridized orbital, mixed orbital. So 1s and 3p mixed together. Imagine like you take 1s and you take 3p and you put it in a blender and you blend them together. If you blend them together, this is what you would get. You would get 1, 2, 3, 4 sp3 orbitals that look like this. This is adding these 4 together in a blender, blending them together, and these are the 4 you are going to get. Okay? Now these 4 new orbitals are going to go and bond with hydrogen. And that's the tetrahedral geometry that we get. And that's how we know this hybridized orbital. So it's not just sharing your orbital, it's sharing this new hybridized orbital. So we have these new orbitals. Now these new hybridized orbitals, the sp3 orbitals, are going to go and overlap with hydrogen, and we get the tetrahedral geometry that we're looking for. One more time. We have an s orbital, 3p, put them in a blender together. They're going to mix together. They're going to generate this hybridized orbital. We call it sp3. Why do we call it sp3? Because it's mixed from 1s and 3p. You blend them together. These are the new orbitals you get. Now these new orbitals are going to go and overlap with hydrogen atom. And that gives us the geometry that we wanted. That will give us the geometry that we wanted. That gave us a tetrahedral geometry. Okay, now let's do the next one. I'm going to keep doing until you understand this for me. And then there's also a shortcut at the end that I'm going to tell you. I should have not said that. Now you are going to fast forward me to the end. BF3. If you draw it out, we've done this before in the other lectures. We drew BF3 geometry out. And the geometry is trigonoplanar. Is it polar or non-polar? It's non-polar. Hopefully you're able to do that pretty quickly. Okay. Now, what is my center atom? My center atom is boron. The electron configuration is helium. 2s2, 2p1. Okay. Now, I'm going to actually draw this out. So I have a 2s orbital. I have a 2p orbital. The 2s orbital has 2 electrons. The p, I only need one of them. 1p. And let's undo that. Okay, this is my boron energy level. Like we said before, boron cannot go and bond with fluorine as long as the boron electrons are not on the same page. So they're going to mix. They're going to mix together. Now here's the thing. How many electrons do I have? 1, 2, 3 electrons. I have 3 electrons. So I need 3 hybridized orbital. So I need them to mix. I need 3 hybridized orbital because I have 1, 2, 3 electron. So what is going to mix? Since I only need 3 mixed orbital, 3 hybridized orbital, one s is going to mix with 2 of these p orbitals. 1, 2, 3. These are going to mix and they're going to be on the same energy level. Why not all of them like last problem? Because I don't need them. I only have 3 electrons, so I only need 3 hybridized orbitals. So I took 1s and I took 2 p's to make this. So what do you think we call this? sp2. sp2 hybridized orbital. Again, nothing fancy. It sounds super fancy. They just mix together. Now they're on the same energy level. So before they bond, before they go and bond and overlap with fluorine, the electrons on the boron, they need to be on the same page. Once these electrons are on the same page, now they can go and bond and overlap with boron. Now they can go and bond and overlap with boron. Okay, now I just added a picture for you guys to see it. So I have 1s and I have 2 p's, again, because I only have 3 electrons, so I only need 3 hybridized orbitals. 1s and 2 p's are going to blend together, put them in a blender, think about it that way, and what I end up getting out of it, I end up getting out of this sp2 orbitals. Now they can go and overlap with fluorine atoms to make a trigonal planar geometry. Now these new orbitals can go and overlap with fluoride atom to make a trigonal planar geometry. Again, they do end up going and overlapping with the other orbitals. So you have these new orbitals before they go and overlap. Ready for next one? Okay, let's do next one. Next one is H2O. Again, H2O, we've done this before. This is how you would draw the Lewis structure, right? What's the geometry? Bent. Is it polar or non-polar? Hopefully you're shouting the answer. That is polar. Okay. Now, oxygen is a center atom. Oxygen is going to have helium, 2s2, 2p4. Okay. So, I have a 2s, 1, 2, 3. I have 2p orbitals. Now, again, this is for oxygen, my center atom. 2 electrons in a 2s. And 1, 2, 3, 4 electrons in my 2p orbitals. Okay, so again, before the oxygen electrons can go and bond with hydrogen, they have to be on the same page, right? Before the oxygen electrons can go and bond with hydrogen, they have to be on the same page. So we are going to mix them up together. They're going to compromise and make up hybridized orbital. Now, here's the thing. How many electrons do I have? 1, 2, 3, 4, 5, 6. I have 6 electrons. Except I only have 1, 2, 3, 4 orbitals. I have 6 electrons, but I only have 4 orbitals. So there's not much I can do. So I'm going to mix the 2s and I'm going to mix all these p2p orbitals together. If I mix them together, I'm going to get 1, 2, 3, 4. What would I call it? I call it sp3 because I took 1s and 3p and I blended them together. Now, how many electrons? 1, 2, 3, 4. I have to double up. 5, 6. I have no choice but to double it up because I only have 1s and 3p's to mix together to make 4 hybridized orbital. So I had to mix them up. Now, this is super cute. When you double them up, you see this is double up, you see this is double up. What those are the lone pairs. Those are the lone pairs. And this is why oxygen has 2 lone pairs, because they had to double up of these orbitals. That's a little cute, isn't it? Just a little bit. Okay. Now, ready for next one? Next one is NH3. Remember, pause me. Do what I just did for water. Do the same thing. Figure out the geometry, the polarity, just as a practice, and figure out the hybridized orbital. Okay, so if you do it, you know nitrogen is in the middle. You have hydrogen, hydrogen, hydrogen. Nitrogen has a lone pair. The geometry is pyramidal. Is it polar or non-polar? Hopefully you're shouting. That is polar. Nitrogen is in the middle. Nitrogen is helium 2s2, 2p3. So here I have a 2s orbital. Here I have a 2p orbital. Okay. Now here is my nitrogen. 2 electrons in 2s. 1, 2, 3 electrons in a p orbital. Again, before nitrogen electrons can go and mix and overlap with hydrogen, they have to be on the same page. So I'm going to mix them together, make sure they're on the same page. I have 5 electrons, but 1, 2, 3, I only have 4 orbitals to mix together. So I'm going to mix the S and the P. They're going to compromise, and they're going to make 4 sp3 orbitals. Again, I took this one and 3 of this, hence is sp3, because 1 s orbital and 3 of these p orbitals, 1 of the s orbital and 3 of the p orbitals mixed together. Okay, I have 5 electrons. 1, 2, 3, 4. 1 has to double up. What did we say? When we double up, what is that? That is lone pair. So that means ammonia has 1 lone pair. And guess what? It does have 1 lone pair. That's kind of cute, right? Okay. Now, so let's go up this to one more to make sure you guys are getting this down. And these hybridized orbital will explain the geometry like I showed you in the last one. Okay. Now, let's do the last one. Now, pause me right now and then do this on your own. PCl5. PCl5. So, hopefully you did pause me. You unpause me now. If you do the Lewis structure, this is what you end up getting. Right? This is what you end up getting. Now, what is in the middle? Phosphorus is in the middle. So, phosphorus is 3s2, 3p3. Okay. So I'm going to have a 3s orbital, and I also have a 3p orbital going on here. And on the third level, I also have d orbitals over there. I'm not going to pay attention to it, but on the third orbitals, I do have d orbitals. So 1, 2, 3, 4, 5. Now, for people who might be a little confused right now, why I added a d orbital. Here, why? Remember, we have a nucleus, and then let me write down 3 energy level. The first energy level has only s orbital. The second one has s and p, and the last one has sp and d orbital. Remember that? That's exactly what I'm doing. So if I'm on a third level, which I'm on a third level here, I also have the d orbital. Second level has only s and p. D orbital has a d orbital. I'm not using it, but I have the d orbitals available to them when I go to the third level. So I have to mix this because the phosphorus electrons have to be on the same page before they can go and overlap and bond with chlorine atom. Okay. How many electrons do I have? 1, 2, 3, 4, 5. I have 5 electrons. Now guess what? Now that I'm on the third level, I have the 1s orbital. I have the 3p orbital. I also have the d orbital to use if I want. Now, 1, 2, 3, 4, 5, I have 5 electrons, so I can mix this, I can mix this, and I can borrow one from the d and mix them all together. Before, I couldn't do that because in the second level, I didn't have the option of using the p, the d orbital. But now, on the third level, I have the d orbital. I could use it. So I need 5 hybridized orbitals. So I'm going to mix them all together. So I get 1, 2, 3, 4, 5. Again, why did I have on 5? Because I have 5 electrons. Okay. Now, what would you call this hybridized orbital? sp3d. Again, look at my hand or my pointer. Because I took 1s, I took 3p, and I took 1d orbital, and I mixed them together. I have 5 electrons, so now I can borrow from the D and I have 5 hybridized orbitals. And a hybridized orbital, like we said before, they will explain what is going on. Okay, so far so good. So hopefully you guys understood all this hybridization. Again, if I had to summarize it for you, so not any two non-metals can just overlap, share an electron, and form a covalent compound. In order for them to do that, they have to overlap. Their orbitals have to overlap. If their orbitals overlap, then they can share an electron, they can form a covalent compound. That's why not every single covalent compound exists out there. But it's a little bit trickier than that. And that not only they have to overlap, the center atom has to have a hybridized orbital, right? Because before they can go and form overlap with anyone, the electrons on the center atom, they have to be on the same page. They're going to mix, they're going to form this hybridized orbital, and now this hybridized orbital can go and overlap with other atoms. Okay, now hopefully you got this down. I want to show you the shortcut now. Ready for the shortcut? But before I show you the shortcut again, I want to make sure you really understand this. Alright, now let's go to the shortcut. Here is the shortcut. Hopefully you didn't just cut all the way to the end of the video to see the shortcut. We have only one s orbital, right? S orbital has 1 room. P orbital has 3 rooms. D orbital has 5 rooms. Okay? Now, single bond, double bond, triple bond, and lone pair, they all count as 1. Okay? You ready for this? Now we're going to go back to PCl5. Now watch my pointer. On my 1, 2, 3, 4, 5. 5 things are around the phosphorus. 1, 2, 3, 4, 5. sp3d1. And that's what we got over here. That works every time. Okay. Now, let me put back the other ones that we drew together. Let's redo all these hybridization using a shortcut. 1, 2, 3, 4 things around carbon. 1, 2, 3, 4. That would be sp3. Okay. How many things around boron? 1, 2, 3 things around boron. Okay. So 1, 2, 3. S and then 2p. sp2. Okay. How many things are on oxygen? 1, 2, 3, 4. Because remember what I said. Single bond, double bond, triple bond, lone pair count as 1. So 1, 2, 3, 4. So 1, 2, 3, 4. It would be sp3. Okay. Last one. 1, 2, 3, 4 things around nitrogen. 1, 2, 3, 4. That would be sp3. All right, so here's the shortcut. You know the shortcut. Now I'm going to post one more video to kind of bring everything together. Here's your take-home problem. You ready? Here's your take-home problem. What I want you to do. Xenon F2. Br F5. HCN. I want to give you one more. Let's give you ICl4 minus. Here's what I want you to do for this one. Do the Lewis dots. Tell me what is the geometry. Tell me is it polar or non-polar. And tell me the hybridization of the center atom. Okay. Do this. That will be a good practice problem for us. Nice job hanging in there.